Welcome to 8.4 part 3. So I'm going to do the same thing I did. I'm just going to set these story problems up in part 3 and then I'll solve them in part 4. So the first one is going to work similar to the last set of them, and then the next two are about distance, rate, time, and I'll talk to about that here in a second. So Juan goes to the bank and gets change for a $50 bill, consisting all of $5 bills and $1 bills. Okay, now there are 22 bills in all. How many of each kind are there? So let's just let X equal number of $5 bills, so the fives, and we'll say Y equals the number of ones. Okay, now if there's 22 bills in all, X plus Y equals 22. So the number of fives plus the number of ones is 22. So we're equating number of bills plus number of bills is total number of bills. Now we're going to equate the money part. Now, since each $5 bill is worth $5, 5x, that denotes how much value we'll have of $5 bills. 1 times y, or 1y, is going to denote the value of the $1 bills. Now we know we're getting change for a 50, so the value of the fives plus the value of the ones should equal $50, or 50 right there. And that's the setup. So we have bills plus bills equals bills, and money plus money equals money. And that is the setup right there. So for the next one, there's a two cars leave Denver traveling in opposite direction. One car travels 80 miles an hour and the other one's at 96 miles an hour. And how many hours will they be 528 miles apart? So the setup on this is a little bit different, but one thing I want to talk about briefly is this. Distance equals rate times time. So if you want to know how far you've gone, it depends on how fast you're going, your rate, and how long you've been going for, your time. So that's what we have right there. Now, if we're thinking about this, I'm going to draw a little picture. Like we have this. Let's say this is Denver. Now, one car is traveling in this direction. One car is traveling in this direction. That's two cars leave Denver traveling in opposite directions, so one goes 80. So let's just say this is car 1, goes 80 miles an hour. Now, 80 miles per hour, that's a rate. The other one's at 96, so this is 96 miles per hour. That's a rate. Okay, so it says in how many hours will they be 528 miles apart? So if we think about how far apart they're going to be, if this car is going this way and this car is going this way, we're trying to find when this total distance between them is 528. Well, because each of them are going at a different speed, they're each traveling a different distance. So let's call this like D. That's not working out to be a D very well. D1, and let's call this D2. So one thing we can say is this. We want to know how long it's going to take for D1 plus D2 to equal that total distance of 528. So we have D1 plus D2 equals 528. Okay? So that's one thing that we have right there. So this is going to be one of our equations. Now, the other equation that we're going to have to deal with, or the other equations we're going to have to deal with, is this. We want D1 and D2. Now, if D equals R times T, D1 is going to equal the rate of the first car. Well, we know the rate of this first car is 80. And the time. We don't know what the time either, because it asks us in how many hours. So we're just going to say T is hours. So the distance that the first car goes is going to be 80t. Now we need to know what d sub 2 is. Well, d sub 2, distance is rate times time. This is the rate, 96. And then it goes for t hours, so that's the distance as well. Now, the way we're going to end up solving this is we have more than a couple equations, but we're just going to use substitution. Plug this in for the d1, plug this in for the d2, and then we'll have equation in time, and that's how we solve this problem right there. And I'll get to that in the second part. Now, the third problem we have is this. It says Donna's late for a meeting. Donna's late for a meeting after traveling from one town to another town at the speed of 32 miles an hour. So I'm just going to draw a picture. This is town 1. This is town 2. So, I'll say trip 1. So let's just read through this. Dawn is late for a meeting after traveling from one town to another town at 32 miles an hour. If she would have traveled 4 miles an hour faster, she could have made the trip in a half hour less time. Well, so there's the actual trip she made, trip 1, where she's going 32 miles per hour. There's a trip 2. This is a hypothetical trip. Now, if she had gone 4 miles an hour faster, that'd be 36 miles per hour. She would have gone in a half hour less time. Now, we don't know how long it took her on the first trip. So let's call the time T hours. So it took her T hours the first time. Now, if she had gone 4 miles an hour faster, which we have right here, that's 36 miles an hour, she could have made the trip in a half hour less time. So her time on the second trip would have been T minus 1/2. So a half hour less time. So the question is, how far apart are the towns? So what we can do is this. We can set up an equation using this distance equals rate times time for the first trip. So the trip 1, the total distance right here we're going to call D. So we could say D equals, well, that distance is going to be the 32, the rate, times the time. So 32 T. Then we can talk about this distance in terms of the second trip. Now the distance would be the same in the second trip. She's just going faster, so her rate's 36. And the amount of time is less, so we have times time, which is T minus 1/2. So that's the setup for this one. Now, what ends up happening is, because D equals 32T and D equals 36, T minus 1/2, we can use the property of substitution and solve this. But those are the setups of these problems. In the next video, I'll be solving them.